If you would recall, yesterday, we introduced a new set of coordinates that we can impose on three-dimensional space. So our new kind of coordinates are going to be called spherical coordinates. All we've been doing, building up from rectangular coordinates, is taking coordinates measured all in distances. In rectangular coordinates, x, y, and z are all distances, and including more angles. So cylindrical coordinates converts one of our coordinates to an angle. Spherical coordinates takes two of our coordinates and turns them into angles. That's as far as we can go. We can't have three coordinates that are angles. That would just define too much stuff. Plus, where do we put the third angle? Yeah, this is pretty much it. We got three distances, two distances and one angle, two angles and one distance. The easiest ones to get a hold of are rectangular and cylindrical coordinates, because rectangular coordinates are just rectangular coordinates in R2 with a z-axis on it. Polar coordinates with a z-axis give us cylindrical coordinates. All we're doing in rectangular and cylindrical coordinates is adding a z-axis to the xy plane or the r theta plane. Spherical coordinates is something that's legitimately different. We only get one distance, so our distance is the distance from the origin to the point in question. But then we're going to use two angles to locate that point. One angle is how much we need to rotate from the positive x-axis, and the second angle is how much we need to rotate from the positive y-axis. So if we think about standing in, I think I use that corner of the room for the origin. There are some boxes, just look past the boxes. 0, 0, 0 would be at the origin, 0 distance away, rotating through 0 degrees from the positive x-axis and rotating through 0 degrees from the positive z-axis. So if we start applying these distances, so if we have coordinates of, let's go with 5, so 5 feet off the ground, up that corner 5 feet. And then we can start rotating through it. Theta is pi over 4. Then from the positive x-axis, we'll rotate 45 degrees or pi over 4 radians. And then our angle 0 would keep that point on the z-axis, the positive z-axis. And then as theta increases, we would just bring down that plane at theta equals pi over 4. So if phi is equal to pi over 6 radians, then I would drop down 30 degrees, and that would point 5 feet away, be about here from the origin, 45 degrees. So it's just a different way of measuring things. Practice, and then we'll get used to it. You'll also notice that we led with spherical coordinates and triple integrals. So as soon as I introduce you to the coordinates and describing places in space, I immediately jump to multivariable calculus and want to start using this in triple integrals. And I go, that's a little bit fast. I remember a good deal of time before we were doing even like single integrals after we learned about x and y coordinates. Because that like happened in the xy coordinate thing happened in algebra. And then integrals happened in calculus, which is some significant amount of time later. Here, spherical coordinates. Spherical coordinates and triple integrals. That was like 5 minutes. Heck, man. Things just speed up. It's hard to be sitting in a math class and hear the words, things are speeding up. All right. Actually, I'm just going to do this from the volume of W perspective, so I don't have to worry about my notation as much. Also, the focus is on setting up the integral, describing the solid W using these sets of coordinates. So we have some already. We know that dV is our volume. In rectangular coordinates, we didn't have to do anything special. Dx was a length. Dy is a width. And dz is a height. X, y, and z all represent distance. So dx, dy, and dz all represent distance. The product of three distances will give us a volume. We had to make adjustments. We had to trade we couldn't just take dy and replace it with d theta, because d theta is not a length. We have to convert d theta into a length with arc length. So r d theta is the arc length for the d theta. dr is a length, so that contributes to volume, and dz is also a length, so that contributes to volume. What we had to do here is arc length to convert d theta into a distance. Oops, I should say since d theta is not distance. Dx, dy, and dz, those can all be meters, but d theta is not going to be meters, it's going to be radians. I have to multiply my radians by meters to get meters. Now we're going to notice the same thing in our spherical coordinates. D rho is going to be a distance, so that's no problem. So rho is distance, but only rho is distance. So in my volume, I can just put d rho, that'll be my length. The next easy one to convert is phi. So notice that if we have a d phi, phi is dropped down from the positive z-axis. And if I draw a right triangle up there with phi, rho is the hypotenuse. So to get phi, d phi to be a distance, I just need to multiply by how far we are from the origin, and that is exactly described by rho. So to turn d phi into a distance, I need to multiply by rho. So there's the arc length. The point is rho units away through an angle of d phi. So I'm just doing the same thing. I need to multiply by how far we are from the origin. Now, the theta that we have in spherical coordinates is the same theta that we had in polar coordinates. So if I have a d theta, I need to turn that into a length. We know that d theta is r units away from the pole. The problem here is that we don't have r anymore. We grabbed theta, brought that up from cylindrical coordinates, but we did not bring r with us. I can't just say r d theta because no one knows what r is. I need to write r in terms of rho, theta, and phi. Preferably rho and phi because we're trying to describe theta. So notice that theta becomes a distance by multiplying by r, but we don't have r in spherical coordinates. So theta becomes distance on multiplication by r. D theta becomes a distance on multiplication by r, but there is no r in spherical coordinates. I guess there is one. There's one right here, but it's not the r that we care about. This r. Well, we don't have r. We have rho, theta, and phi. But if we go back up to our picture, notice that r, this distance is the same as this distance from the z-axis to our point. Okay. That r on the xy plane is being, if that distance down there is the distance from the z-axis to the point parallel to the xy plane. I need to write that in terms of rho and phi. And notice that it's in the same triangle with, in a triangle with phi and a hypotenuse of rho. So it's just the, what would, we would normally call the vertical components because it is opposite the phi. So the r is equal to rho times the sine of phi. That's how far the point is from the z-axis, parallel to the xy plane. I can just say that's how far rho is, the point is from the z-axis. And that's what I need to know because that's how, that r is how we turn theta into a length. So we have length times width times heights, and our height is going to be rho times the sine of phi times d theta. I need to use arc length since d theta is not distance. And I need rho sine phi because that's r in terms of rho and phi. In cylindrical coordinates, we had r. That's how far we are from the pole. That's what we need for the distance. I still need that distance, but I don't get to use r because I don't have that coordinate in spherical coordinates. I need to write r in terms of rho and phi. So cleaning this up, we've got this extra factor of rho squared times the sine of phi, d rho, d phi, d theta. I've got this extra factor of rho squared times the sine of phi. Then I have the d rho, d phi, and d theta. Yeah. Correct. So when we haven't described anything yet. This is just to fill in this dv part. Because remember, we have to have the f of x, f of rho, theta, and phi times the dv. We're just making sure that our dv represents what we claim it's going to represent. dv is supposed to represent a volume. I can't make a volume out of d rho, a distance, and two angles. So then I'll just have meters times radians. That's just meters. We needed to turn d phi and d theta into meters, into distance. And to do that, we needed to use arc length, and so we need this extra factor. TLDR, if you are doing a triple integral in spherical coordinates, you need a rho squared sine phi. As usual, my class, 2 minutes of information packed into a half an hour. Made me realize why I play D&D. I've heard D&D described as 30 minutes of fun packed into 4 hours. Any questions? Comments? I sometimes wonder if math teaching happens sometimes on certain levels, like this amount of explanation happens because it's a variation on the, well, I have to suffer, so you have to suffer too. Like if your friend sees something really awful on the internet or something like that, the first thing they do is share it with you, right? It's like, oh man, this was a really unpleasant experience. Here, watch. Right? Everybody has a friend that will do that to them. Maybe you are that friend. If no one's ever done that to you, you're the one that finds the nasty stuff on the internet. You are the problem. So just take heart in the fact that you're filling an important role in your friendship. You're like, oh, this is disgusting. This is an awful experience. I need to share this with my friends. Guys, check this out. Why did you show that to us? That was awful. It's like, oh, at some point, after, of course, I took Calc 3, at some point it kind of made sense where this rho squared sine phi came from. Because my Calc 3 instructor essentially says, oh, well, there's a rho squared sine phi that you need to throw in there. And most of us, and some of us, not me, because I would never raise my hand and ask a question in class. Actually, I wasn't ever in that class anyway, so it's kind of irrelevant. But some people are like, oh, well, where does that come from? And I just imagine the instructor's kind of like, and then the students are like, oh, never mind. And then in his mind, the instructor's like, oh, yeah, that worked. Yeah. Sometimes you just don't want to explain something. You know what I mean? It's kind of like the instructor's version of go ask your mother. Kind of like pass the buck. It happens in written form too. Some of you might be reading a math book in the future. I don't know. I don't know if you know this, but math books actually can be read. You could like look at the words on the page and actually read them instead of just like look for the example that looks like the one that you're trying to do and copy it and like change the numbers around. You know what I mean? You know exactly what I mean. I can tell because you're math students. Ask me how I know. But you can actually read these things. There's information in them and shit. It's like, whoa. So anyway, you're reading the book and then it's like, oh, here's a proof. Or here's a theorem. And you're like, oh, normally after a theorem, they give us a proof, right? That makes sense. They make a claim, then they prove the claim. But sometimes they're like, oh, the proof is left as an exercise to the reader. I'm like, oh, did this book just look at me and say, go ask your mother? Son of a. Anyway, what are we talking about? Oh, yes. So I think at some point, this rho squared sine phi finally made sense to me. And I'm like, oh, now I have to tell everybody about this. You know what I mean? It's like when something finally makes sense to you and the opportunity comes up and you just like, ah, I have this one. Now's my time. You know what I mean? Because otherwise you're just sitting on this information and it never comes up. No one in any of my campaigns is playing a soul knife rogue, so I don't get to use my explanation of why you don't get to use psychic blades as a reaction. I'll try to spare all of you from that. It's really hard to resist because it's so clear. It's because you have to take the attack action to manifest the psychic blades. Now, if they wanted you to be able to use them like a normal weapon as a reaction, instead of saying that they manifest when you take the attack action, they would just say, use your action to manifest the weapon or use a bonus action to manifest the weapon, like the Hex Blade. Everybody who is trying to rule on Soul Knife Rogue, read Hex Blade, where you actually manifest the weapon, where it's just in your hand the whole time. Do you know what I mean? The intent is exceptionally clear. They said attack action because you can't just manifest it unless you take the attack action. Now, if as a DM, you want to rule that a Soul Knife Rogue can manifest their psychic blades as a reaction when performing an opportunity attack, that is perfectly reasonable. I think giving the rogue 2 opportunities to deal sneak attack damage as psychic damage is a little bit overdone, but that's your table. You know what I mean? That's all. Incidentally, there's nothing in the wording that says you wouldn't be able to use extra attack with your psychic blades because you're taking the attack action. But they clearly did not want you to use it on reactions. Otherwise, they would have just said, you manifest psychic blades. QED, bitches. That's from my new series, Evan Leach, Rules Lawyer. I object. Anyway, what are we talking about? Oh, yeah. We got to find the volume of a sphere in spherical coordinates. Now, if you're thinking this is going to be pretty simple to find the volume of a sphere in spherical coordinates, it seems like it's tailor-made for finding the volume of the sphere. You are 100% correct. All right, we're making a triple integral. So I need 3 of them. We're trying to find the volume of a sphere. So I'm going to take this triple integral and use the integral to describe the sphere. Since I just want the volume of the solid I'm describing in the integral, I'm going to integrate the function 1. But this is going to be a triple integral in spherical coordinates. So I don't just get to write dv, I have to break it up with d rho, d phi, and d theta. And to make sure that that still gives me a volume, I need to have this factor of rho squared times the sine of phi. I'm going to make it in purple to make sure it's part of the dv. Even though when we go to integrate it, that's part of the integral. In the setup, it's part of the dv. That's how we're thinking about it. But when we go into the mechanics, it's going to be part that we have to integrate. You may notice that I'm being a little bit cavalier about the order that I'm tackling things. If you were thinking that setting up the volume of a sphere in spherical coordinates is going to be pretty easy because spherical, it's like right in the name. The reason for that is describing a sphere in spherical coordinates is just going to be 3 intervals. Just like a rectangular solid is 3 intervals, just like a cylinder in cylindrical coordinates is 3 intervals, a sphere in spherical coordinates is going to be 3 intervals. We're just redefining what we think of as a box. So if I write d rho first, the radius of the sphere was r, so rho will start off at 0 and go out to the radius of the sphere, capital R. D theta is going to be how far we go around from the positive x-axis. We want to go all the way around the circle. So theta will go from 0 to 2 pi. Now I've got to describe d phi, the interval that we have d phi. Now remember, phi equals 0 is pointing directly up. Phi is the angle that we make with the positive z-axis. So 0 is pointing straight up. And we want we want the whole circle. So we'll go phi all the way down to pi. Notice that we're not going to go from, take phi from pi all the way out to 2 pi. Because I just need that front half, because I'm taking that front half and rotating it all the way through, all the way around. So since I have theta listed from 0 to 2 pi all the way around, I don't need phi to go all the way around. I just need phi to do that front half. So I'm going to take that semicircle and rotate the semicircle around. So phi goes from 0 to pi. Now we can see how our integration is going to go. We're going to integrate rho first. The integral of rho squared is 1/3 rho cubed. That's where our radius cubed is going to be coming from. There's also where the 4/3 is going to be coming from in the denominator of 3. The next integral is going to be a theta integral, which is going to introduce theta as a variable. That's getting plugged from 0 to 2 pi. That's where our pi comes from. And then the last thing we're going to have is the integral of sine of phi with respect to phi. It's going to give us a cosine of phi. And we're going to go from 0 to pi. It's going to be a negative and a positive. Stuff's going to cancel out. 4/3 pi r cubed. No trigonometric substitution. Don't even have to do a regular substitution. This is just all basic integrals. Any questions? If you want to make sure that you don't understand what's going on, all you have to do is take my word for it. It's rho squared sine phi. Just have to include that in the dv for your spherical coordinate triple integrals. And phi goes from 0 to pi. I just take Leach's word for it. That's the best way to make sure that you don't understand what's going on. If you want to make sure that you do understand what's going on, you have to be able to explain where the rho squared sine phi comes from, why we have to put it there, where it comes from. You have to explain why we're going from 0 to r in rho, 0 to 2 pi in theta, and from 0 to pi in phi. With that information, you got to try to come up with a different way of describing this sphere in spherical coordinates. Here's the way I chose. Is there another? Probably, since I even brought it up in the first place. Any questions? Comments? Snide remarks? How's everybody okay? All right. That's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.